We see electric cars on the road all the time now, right? But the real revolution, the thing that's changing everything, it isn't just that quiet hum of the motor. It's happening deep inside the battery. Today, we're going to dive deep and explore the incredibly complex, hidden world of a single EV battery cell.
So what is the hidden key to an EV's power? I mean, really, what dictates its range, its performance, and even its safety? Well, the answer isn't just the big battery pack you see. It's actually this intricate dance of chemistry, physics, and engineering happening at a scale you can't even see. Let's get into it.
Think about it. For more than 100 years, the internal combustion engine was this masterpiece of mechanical complexity. All those pistons, valves, and gears. And then you look at an EV, and on the surface, it just seems so simple. But, that's really just an illusion. While the electric motor itself is pretty straightforward, the battery that powers it is anything but. Yeah, this is way more than just ripping out a gas tank and dropping in a battery. We're talking about a fundamental shift to these incredibly sophisticated, high-tech energy systems. An EV battery isn't just a bucket of electricity. It's an active, complex system that has to deliver power safely and efficiently for years and years. Okay, so if you break down an EV's powertrain, it really comes down to three main components. You've got the electric drive, that's the motor that actually turns the wheels. Then you have the power electronics, which are kind of like the brain, managing how all that energy flows. And then smack dab in the middle of it all, you've got the battery. It's the powerhouse for absolutely everything in the car. So to really get what makes these things tick, we have to go on a bit of a journey. We're going to zoom in, like way, way in. We'll start with the car itself and drill all the way down to the very heart of the battery, the single individual cell. All right, so let's start big picture. Here's the car. It looks pretty familiar, right? But believe me, under that shiny paint, the whole architecture is completely different from the gas-powered cars most of us grew up with. Okay, now let's look underneath the car. See that big flat panel? That's the battery pack. And putting it there on the floor is actually a really smart design choice. It opens up a ton of space inside the car, and get this, it lowers the center of gravity, which gives the car that awesome grippy handling. But this pack is really just a protective shell. And this is what we're here for. Inside that big protective pack, you've got hundreds, sometimes even thousands, of these individual battery cells. This little guy right here, this is the fundamental building block. Everything, the performance, the range, the safety of the entire vehicle, it all starts with the engineering that goes into this one single cell. But here's the thing, not all cells are made the same. Automakers basically have three main shapes to choose from. You've got your cylindrical ones, pouch cells, and prismatic cells. And believe it or not, just picking one of these has this huge ripple effect on the entire car's design, from how the battery pack is shaped to how it's cooled, and even how the car is put together on the assembly line. So how on earth do you engineer something this complex? I mean, you can't just build 1,000 different physical prototypes. That would take forever and cost a fortune. So instead, modern engineers do something brilliant. They build the entire battery inside a computer first. They create what's called a digital twin to test and perfect it before a single real part is ever made. The magic behind this is something called multiphysics simulation. Okay, think of it like this. Instead of testing just one thing at a time, powerful software platforms can model everything at once. We're talking the electrochemistry, the heat buildup, the physical stresses on the materials, all interacting with each other just like they would in the real world, all in one virtual space. What you end up with is this perfect virtual copy, the digital twin. And this lets engineers do things that would be way too dangerous, way too expensive, or just plain impossible in a lab. They can push that virtual cell to its absolute breaking point, safely, all with a few clicks of a mouse. And trust me, they absolutely push it to its limits. Every new digital cell design has to go through what you could call a virtual gauntlet. It's the series of super intense trials designed to test every single aspect of its performance and, its toughness. Okay, test number 1, electrochemical performance. This is all about the cell's day job. How well does it store and release energy? The simulation gets right down to the nitty-gritty, tracking how individual ions move around. This is what tells you everything about the car's potential range and its acceleration. And this brings up a classic engineering trade-off. See, a 1C charge rate means the battery goes from empty to full in about an hour. If you double that to 2C, you can get a full charge in just 30 minutes, which is awesome, right? But That speed generates a lot more heat, and heat is the enemy of a battery's long-term health. Simulation is absolutely crucial for finding that perfect balance, that sweet spot between charging fast and making the battery last. All right, next up, the cell has to prove it can take a punch. It's not just a little electrical box, it's a structural part of the car. It has to handle years of road vibrations, potholes, you name it. And most importantly, it has to stay safe and intact if the worst happens, in a crash.
So to make sure it's tough enough, the simulation basically puts the digital cell through the ringer. It gets virtually crushed from the top, bent in the middle, and squeezed from the sides. Engineers look at exactly how it reacts to all these forces to guarantee that the design is strong enough to handle real-world impacts without failing.
And now for the final and maybe the most critical challenge of all, the test of time. An EV battery is a huge investment. It needs to last for years, for hundreds of thousands of miles. So how can engineers possibly know how it's going to perform 10 years down the road?
Well, the big enemy here is something called degradation. And it basically happens in two ways. There's calendric aging, that's just the battery getting older, sitting there day after day. Then there's cyclic aging, which is the wear and tear that comes from using it, charging it up and draining it down over and over. Both of these slowly chip away at the battery's ability to hold a full charge. And this is where it gets really mind-blowing. These simulations are so powerful now, they can actually model the tiny, microscopic things that cause this aging. They can predict stuff like the growth of these unwanted chemical layers that basically trap lithium ions. Or they can foresee these tiny little stress cracks forming on the surface of the materials. By seeing these problems happen in the virtual world, engineers can design cells that fight back against them from day one.
Okay, so simulating all that microscopic detail is, as you can imagine, incredibly complex. A single, super detailed simulation could take a powerful computer days to finish. That's just too slow. So to speed things up, engineers use this really clever trick called model order reduction. Think of it like creating a super accurate summary or a shorthand version of the battery. It captures all the important physics, but lets them run these complex aging simulations in just a few minutes instead of days. It's a total game changer.
All right, let's zoom back out for a second. We've been deep in the virtual world, but what does all this intense digital testing actually mean for you, the driver? How does a bunch of code on a computer screen translate to a better car on the road? This is where the rubber meets the road, literally. When you optimize the electrochemistry in a simulation, that directly leads to faster charging times and longer range in the real world. When a cell passes all those virtual stress tests, that means you get a physically safer battery that protects you in a crash. And when you can accurately predict degradation, well, that means engineers can design a battery that's going to last you for a long, long time. You can draw a straight line from every virtual success to a real-world benefit. And this all leads to a really powerful idea to wrap things up. The ability to model, to test, and to completely perfect something as ridiculously complex as a battery cell in a virtual world before you even build a single physical one, that is a massive leap forward. So the real question isn't just about making better batteries anymore. It's, if we can do all this for a battery, just imagine what this kind of simulation power is going to let us design next.